Okay, example 4, find the points on the parabola. So we're looking for possibly more than one answer. On the parabola, so here's our function, f of x, that are closest to the point 0, 3. Okay, first, let's do a sketch. Here is my grid. What does this function look like? Downward parabola, vertex at 6. Okay, so this is my picture. Where is this point? 0, 3. So it's halfway between the vertex and the x-intercept, right? So this is the point of interest. How many solutions do you think we're going to get? How do you know? It's symmetric, right? So whatever point we find on the right side must be the same point on the left side because we have a symmetric looking graph, okay? So we are expecting 2 solutions. Now, when we're looking at the closest point, what are we looking for? Again, remember we're doing derivatives and we're looking for peaks and valleys. The closest point to 0, 3. What are we trying to find? Think of the language. Look back at example 3. How did we identify, or example 2 or whatever? Are we looking for a minimum or a maximum? We're looking for a minimum what? We're looking for a minimum. A minimum what? Okay, let me ask it this way. Yes, distance, right? This is a function that gives us a parabola. We know that this parabola doesn't have a minimum. So obviously that's not the function we're worried about. What we are worried about is the distance between the parabola and our point of interest. Now think back to grade 11, grade 12. How do we find the distance between 2 points? Yes, which is? Square root. Yes. Okay, so I'm going to call this capital D is the square root of x minus x. Okay, let's call this x1, x2, all squared. y1 minus y2, all squared. So we want coordinates, the distance between the coordinates, right? Because what we're doing in reality, if I just zoom in on here, this has an x coordinate x1, y1. This has coordinate x2, y2. And you can see that this is a right triangle, right? And a squared plus b squared equals c squared. We're looking for the distance, your c squared in this case, of that triangle, okay? So anytime you have 2 points, we use Pythagoras to find the distance between them. Now, we know 1 point. We can label that as x1 or x2, doesn't matter, you pick. The other point, however, we have a function, right? So when I go to substitute here, I'm going to use the coordinate I know and the function that I have. So let's say x minus 0 squared plus y minus 3 squared. However, when we do derivatives, we want to have single variables in our equation. Yes, sir. Absolutely. That is exactly what I'm going to do. I'm going to take this equation, y equals 6 minus x squared, and I'm going to substitute it in here. So then my entire equation is only in x's, right? Okay. So let's do that. And you can see this is a distance that depends on the coordinate x. This is going to be x squared plus 6 minus x squared minus 3 all squared. X squared minus, was it 3 minus x squared all squared. So this is now my function. Now, yes.
What minus?
Oh, sorry, that was supposed to be plus. Thank you. If I do the derivative, I can go ahead and do the derivative here. However, I have a square root, and inside the square root, I have a sum of functions, and one of those functions is a function inside a function as well, right? So this is like a triple chain rule, which is ugly. So what I'm going to try to do is simplify the inside a little bit more, okay? So let's just expand that bracket. Let's try to make our derivative calculation as simple as possible. If I expand this, this will be 3 squared minus 6x squared plus x to the 4. Can you double check that I did that right? Yeah, okay, so let's put the x squareds together and the x4. So this is x to the 4 minus 5x squared plus 9. Okay, that's a little bit easier. Okay, so now when I do the derivative, I've got a much simpler thing to look at. Here is a pro tip. Pro tip. When minimizing or maximizing, okay, I'm just going to call it a max, a radical, we only need to minimize or maximize the radicand. What's the radicand? What's the radicand? The stuff on the inside, right? So because if you know your maximum inside number, then the square root of that maximum is still going to be a maximum, right? If you know the minimum of the inside number, then the square root of it is still going to be a minimum, right? So it follows suit. It doesn't, a radical does not change the sign of the function. It just changes the value, okay, by taking the square root. But a max is still a max, and a min is still a min. So this becomes even easier because now I'm just going to focus on what is inside the radical. Okay, so let's take a look. D prime is going to be 4x cubed minus 5x squared. That's it.
What's the just power? Or negative 10?
What did I do? I didn't derive it. Oh my gosh. 10x. Okay. Now remember the mistake Miss Gordon did yesterday. Is that for me? Oh, bonus sticker for Barnur. Got me coffee.
You said you wanted it.
I did say I wanted it. Because you know how many times I tell grads that I want something and they just show up? Yeah, I'll give you an extra sticker. Don't leave without it, okay? 2 stickers today. Thank you. Okay, I'm going to have a little treat while you tell me what we're going to do next. If I need to make this 0, right? Minimizing means I'm finding peaks and valleys. What am I going to do first? Oh, yes, thank you, Gulsheen. We have to factor first. So let's factor. This is 2x, x squared minus 5. So my possible options are x equals 0 or plus minus 5/2. Thank you. Okay, we have 3 possible options. And again, as we did yesterday, you can use D prime to figure out what is the derivative between these 2 points? Ah, what's going on here? Don't do that. -5/2. Okay, so we can test what is d prime of, I don't know, -5/3. So that would test this location here. No, that would be this location. My bad. Or we can do the second derivative. I think the second derivative in this case will be a lot easier because we would have to test 1, 2, 3, 4 points. Let's not and say we did. Let's do the second derivative test. Okay. D double prime. What is it going to be? Lovely. Okay. Let's test it out. D double prime of 0 is -10. Remember, you're not interested in the number. We're just interested in the sign. It's negative. Yes, it is -10. You're right, but I'm more interested in the negative. Negative means it's what direction? Concave down. Okay, let's check the next sign. D double prime of square root 5/2. It should be positive, yes. So this tells me I have a smiley face. Oh, wrong spot. Okay, without testing the last one, can you tell me what shape it's going to be? How do you know it's a smiley face? Because it's a symmetric graph, right? Plus 5/2 minus 5/2 is the same location on either side of the y-axis. We know it's symmetric about the y-axis. So if one side is a smiley face, the other side is a smiley face. So I don't even have to test it. So our minimums are located at the points root 5/2, tell me what the y coordinate is, and negative root 5/2. Take those two x values, bless you, put it in the original equation. The original equation way up here, right? Because we're interested in where is it located on the parabola. 7.5? For which one? Oh, I guess for both, right? Because that's the y value. 7.5. Beautiful. Okay, so again, visually looks icky, but when you actually go to do it, it's not that bad, right? Any questions about this one? Yes. Because it's a parabola and there was no horizontal shift. The vertex of this parabola is at the coordinate 0, 6. So the distance is this pink line. We are looking for the coordinate on the black line. So the pink line is telling me where the x coordinate is. The black line tells me where the y coordinate is. So this is root 5/2. Yeah? Okay, so the distance is telling us what is the shortest distance, where on the x-axis is the value that gives us the shortest pink line. We use that value on the x-axis and we put it into the equation of the black line to find the y coordinate there. Yes. Okay. Let's do a quick side note here. Let's say you have a function like this. Okay, a parabola, any random parabola. Let's say that in this parabola you have a maximum at, I don't know, 9 or 0, 9. Yeah? Following me so far? then when I take the square root, so let's call this f of x. If I were to draw the square root of f of x, it would look like this. The zeros stay the same because the square root of 0 is 0. Where would the maximum be? What's the square root of 9? 3. Can you see how it's still a maximum? All we're doing when we take a square root of something is taking all the values in f of x and square rooting them. Okay, so let's say you have a function that has, I don't know, let's say -2, -1, 0, 1, 2. Let's say your y values are, I don't know, 4, 9, 0, I don't know, 9, 4. Doesn't really matter. When I go to square root it, my x values don't change, but my y values then become square roots. 2, 3, 0, 3, 2. Where's my highest y value? Here. Where's my highest y value? Here. Do you see that? Okay, so if I can figure out what is inside the radical, what's the highest number inside the radical, when I go to take the square root, it's still going to be the highest number. Yeah? Sometimes you just got to stare at it for a bit. It'll eventually make sense. You just got to absorb it. Hi, yes. Say again. Why did we figure out the concavity? The concavity tells me where my mins and max are. Where it's concave down, I have a max, and where it's concave up, I have a min. And this question was asking us, where are the minimums? So concavity tells us where the minimums are. Does that answer your question? Good. Any other questions before we move on? Good. This is a good test question. Hint, hint, nudge, nudge. Question 5. Okay, find the area of the largest rectangle. Okay, before we keep reading, what is the area of a rectangle? Length times width. That can be inscribed. Inscribed means drawn inside of a semicircle radius r. So let us draw a picture. Here's the XY plane. Let us draw a semicircle. Oh, that was ugly. Let's try again. Oh, I can't get it symmetric. Okay, I'm going to try one more time. Gentlemen, cut it out. Okay, here's the semicircle. Can you tell me the coordinates of the things I just drew? The 3 points, what are they? From left to right.
Is it negative r0?
Mm-hmm.
Or and then r0?
Beautiful. We don't know the value of r, but because it's a semicircle, all of these points are the radius, right? Okay, so we know that part. Now we want to draw inside of this. I'm just going to zoom in here. I want to draw a rectangle inside of here. Right? Rectangles are all 90 degrees. See, this is why I'm trying to draw a perfect semicircle. Let's try one more time here. Just want to touch the corner. There we go. That's prettier. Okay, we want the largest area. What can you tell me about this rectangle and its dimensions? Yes, we know that the radius must reach that corner. What else can you tell me? These are right angle triangles, okay, so we have some symmetry here. Think about length and width. Look at the length and width. What can you tell me about these two coordinates? They are the same. Yes. So let's call this width, and length. Or if you don't like that, you can call the bottom one lengths and the top ones width. Or you can say X's and Y's. I don't really care. Label them however you want. Letters are letters. Okay. So we know that the area of a rectangle is length times width. Looking at the picture that we drew, how would I write it using the variables I have? 2WL, right? How would I write R? R is the hypotenuse of my little triangle in the corner, right? R is a constant, not a variable in this case. Let's assume R is 5, okay? We're not going to worry about it as a variable. We're going to think of it as a constant. Now, how do we put these together? Which equation are we trying to maximize? Area. We want this as a function of one variable. Which variable do we want to use? Let's use width. Okay, so if I were to rewrite this as area, a function of width, I would have 2W. How can I rewrite L? Yes, L is the square root of R squared minus W squared. So this is the square root of R squared minus W squared. Okay, and now that we have the equations, we have a picture, let's get to doing the mathy bits. We want this to be a maximum. What do I do? Derivative. This is a product rule and a chain rule. However, you could, if you wanted to, square the 2 and the W, put it inside of the radical and make it one thing. Yes, Koshi?
Are you taking R as in the variable or
Constant.
constant?
Yeah, we're treating R as a constant, not a variable. So R is not an implicit function. Treat it as a number. Ignore it, essentially. Okay, choose the method for derivatives, whichever one you like. It's totally up to you. Tell me what you get once you've simplified it. Did I make a mistake already? You guys still doing okay? Are we happy with this? Getting something similar, good. Okay, so this is a prime. To find the peaks and valleys, we want this to be 0. When we have a fraction or a rational function that is 0, what are we focusing on? Numerator. 2r squared minus 4w squared must be 0. We are focused on w, treating r as a constant. W equals square root r squared over 2, plus minus, right? Don't forget that part. Or you can think of it as plus or minus r over root 2. That would be all right as well. Okay, if this represents w, which one, without doing a test, are we going to use? What does w represent? Can width be negative? No. So the value that we're looking for is the positive version of this, right? So the value of w is r over root 2. Actually, instead of erasing it, I'm just going to leave it as plus minus because mathematically that is the answer. But we are going to use w is positive. I'll just write it out because width, it's a value. When we go to plot it, right, we'll have the coordinate positive r over root 2, negative r over root 2, but like the actual value of the w is r over root 2. So then last step we need is L, which is the square root of r squared minus r squared over 2. Oopsie, L is 1r squared minus half an r squared. Half an r squared, so r over root 2. Does that make sense? Going back to our picture, does it make sense that L and W end up being the same value? If you think of physics, when you're going to shoot something like a projectile motion, what's the projectile motion angle that you're going to shoot it at to give you the most range? Which will also give you the largest area. So if you're at a 45-degree angle, that means you're halfway up on a unit circle, which means it is a symmetric rectangle. So you end up with 2 squares, make the largest area for the rectangle. Okay, that makes sense. Can I show you a way that you could do this in way easier? Thinking of the unit circle. So this is how we would do it if we just drew a picture, length and width, off we go. Did you have a question? Okay. So I'm going to show you, I'm going to switch colors here in green. Slightly easier way. I spelled easier wrong. Every time. Easier way is trig. Oh, geez. You're so angry. Okay, here's your semicircle. And your R, we're still going to use the idea of symmetry here. Now knowing all the things that we know, but I'm going to use theta. Oh, that's really hard to see that. Theta, not much better, but okay. Where this coordinate is, what is it? R cos theta, R sine theta. The reason I'm writing R next to the cos and sine is because I'm assuming, I can't assume this is the unit circle. If it was a unit circle, then R is 1, it's just cos and sine, right? But if it's a larger circle, then I have to include the R here. So then this and this are now represented with trig. right? So we have the area is 2r cos theta times sine theta. Oops, squared. Yeah, thank you. R is cos theta, R sine theta, so R is just squared. So then when we take the derivative, ooh, actually, do you have your formula sheets with you? Somewhere. Someone has, in your formula sheets, I have some double angle trig identities. Can you find it? Can you see if this is a trig identity? Check your formula sheet.
Two angles from one if it were to be anything.
I think it's a double angle identity. I think that one's what it's called.
Right, but that's the theta is the same angle.
Theta is the same angle, yes.
It's not a sheet on picture, it's not.
It's not on your sheet? Oh, I'm sorry. Okay, well, we'll add it. Okay, this is a trig identity. This is r squared and it's sine 2 theta, which will then make your derivative way simpler. You don't have to worry about fractions and radicals as you go on. Sorry, this is not a prime. This is just a. And so then a prime, remember r squared is just a number, so we're ignoring it. This is r squared cos 2 theta times 2. And then where is cosine 0? Where is sine or cosine 0? $90 angles. So this is pi by 2, which means theta is pi by 4. Hey, look, that's 45 degrees. I'm done. Look at that, cute little 4 lines, right? Compared to all that. Right? And then you guys know how to do, right? Sine and cosine are going to be the same value at pi by 4. Do I need to keep going or are we okay? You see the symmetry? I know, pep rally took it out of us. Okay, let's do the last example. Last example. Oh, look, another wonderful, good question. Hint, hint, nudge, nudge. A cable television company is laying cable in an area with underground utilities. 2 subdivisions are located on opposite side of Willow Creek, which is 100 meters wide. The company has to connect points P and Q with cable, where Q is the north bank 1,200 meters east of P, and it costs $40 a meter to lay the cable underground and $80 per meter to lay the cable underwater. What is the least expensive way to lay the cable and connect the two? So if it were the same cost to connect, then the shortest path between P and Q is just a direct line, right? But it costs double the amount of money to bury the cables in the water than it does to bury the cables in land. So we have to have some combination of land and water. Now it could be, let's run it into the ground here and then run it under the water here. That's totally a possibility. However, there is a chance that we connect it somewhere here, where part of this is on land and part of this is in the water. And I'm drawing it in such a way that hopefully you see some geometry. This is a right angle triangle. Okay? Let's call the unknown part of our triangle X, or A, or C, or whatever letter you want to use, does not matter. It's an unknown variable. How would I label the yellow highlighted portion? Wonderful. 1200 minus x. Okay, how would I label the pink line? It is the hypotenuse, so this would be the square root of 100 squared plus or minus x squared. Plus. Okay, so here are the parts. Now, if I am looking at how much this is going to cost me, C of x, how would I write this? It's $40 on land and $80 in the water. So $40 per meter times the amount of meters on land. So this is 1200 minus x, right? And plus 80 times the length it would be underwater, right? We can slightly expand this. 4,800, 3 zeros, minus 40x. And I don't think I can do anything with the 80 stuff. I can put it in, I guess, but it doesn't matter. Okay, so this is C. I want to find the distance that will minimize my cost. So again, we're looking for minimum, so that means I'm looking for C prime. Okay, this is going to give me, what's the derivative of the first bit? That's 0, so this is just negative 40. And then what would be this derivative? Correct me if I'm wrong. We're good? Lovely. Okay, 2 cancels out the 2. So my final answer is that the derivative is 80x over 100 squared minus x squared minus 40. Okay, yes. I canceled out the 2, yeah. It would have been the same thing. It is a plus x squared. My pen's just not very sensitive today. Okay, are we happy to move on? We are setting this to 0. So then 80x root 100 squared plus x squared equals 40. 80x equals 40 root 100 squared plus x squared. 2x equals the square root of 100 squared plus x squared. 4x squared equals 100 squared plus x squared. 5, nope. 3. 3x squared, is that what I'm looking at? Yeah, okay. 3x squared equals 100 squared. So x is plus or minus 10 root 3. Is that about right? Oh, yeah, sorry. It's 100 squared, square rooted, so it's 100. Yes, sorry, thanks for catching that. Okay, these are our possible values. What makes sense? Do I need to check both of them? Just the positive, right? I can't have a negative length. It's got to be a positive number. So I know that I'm going to just check the positive value for this amount. So I only have one critical point. Do we need double prime? Let's see. What would be the easiest way to test this? I think if I just threw that in my calculator. Okay, let us check that this is indeed a maximum, or sorry, a minimum by doing C prime of, I don't know, what's less than this? 50? And C prime of, what would be more? 100. Sure, we can do 1 and 100. Remember, you're looking for positive or negative. So you're going up to C prime, put 1 in there. You can even put 0 in there, right? 0 is smaller. Might be easier if you did 0. If I put 0 into C prime, I get a negative answer. It means my function is decreasing. If I put 100 in there, I get a positive number, so it means it's increasing. Okay, so we have found the minimum, right? We always need to confirm. Don't ever take the critical points for granted. So, conclusion, therefore, x must equal 100 over root 3. So then the distance on ground, oops, not ground, on ground is going to be 1200, right? It was 1200. Yep, 1200 minus 100 root 3. And you can just throw this in your calculator. I'm going to help you out today. It is 1,142.27 meters. So that is the distance on the ground. And then distance in water, or H2O, is going to be the square root 100 squared plus 100 over root 3 all squared. And this ends up being 115.47 meters. So if they use these distances, then that will minimize the cost. However, I haven't fully answered the question yet. What is C? $40 times the distance on the ground plus 80 times the distance in the water. I'll let you do that one. It's going to be a big number. Starts with a 5. Too high. Too low. Too high. Too low.
54,000.
Too low. Too low.
54,000.
54.
60.
Too low.
90.
380.
No.
300 something.
Higher.
400.
400.
Higher.
500.
Higher.
600.
Higher.
800.
Higher.
900.
Yes. Next.
9.
Nope. Low.
8.
Low.
5.
2.
5.
7.
Low.
0.
Low.
3.
Low.
4.
Low.
1.
Sorry. High. I meant your number was low. Higher. Higher.
4.
Higher.
8.
Yes. There you go. Okay, so we're done this lesson. Your next quiz is, I don't remember where, but there's a calendar posted somewhere. You are now ready to do all of your homework. And look, I didn't even put that many questions on there. We're absolutely doing a lesson tomorrow. It's going to be so relaxing.